Hi, this is the Group 13's final project. Starting with question 1. For question 1, the way we went about this was we created a MATLAB code and we transferred all of the Excel raw data and log transformed it on the code. And then we used the equation f equals m over n plus 1 in order to iterate the values for each amount of data for station 0, the northern station, and the southern station, and then graph that as the normal PDF, or CDF, I mean. This is the northern station and the southern station. And this is a CDF combining all three of the stations onto one graph. And as you can see, there's a big gap between the northern and southern stations compared to the 0 station. So we conducted a hypothesis test between the northern and the southern stations in order to determine whether or not one was higher than the other. For the hypothesis test for the northern station, we took a significance level of 5% for the type 1 error. And for both stations, we only took the data for station 15 for the northern and southern station and calculated the mean, standard deviation, and the sample size. We used the one-sided hypothesis test because we wanted to see if the TC falls under the population mean or if it does not. And we conducted the null hypothesis, as you can see, and the alternative hypothesis. And the results for the northern station were that the z-score equation calculated that it falls outside of the significance level of 5%, and therefore we reject the alternative hypothesis, and that TC grows above 341. We conducted the same procedure in the same test and used the z-score equation once again in order to calculate the hypothesis test for the southern station. And the results we got for this one was that the z-score equation gave a value of negative 6.106. And this also falls outside of the significance level of 5%. Therefore, we have to reject the alternative hypothesis, and TC grows above 341. So in fact, the northern station is above the southern station. Addressing question 2 now. Question 2, we again used the MATLAB code, and what we did was we graphed all of the stations, station 0, the northern station, and the southern station, using the CDF function to the right, and we graphed that data in order to get these values right here. So the red curves are the log transform curves, and the black ones are the original CDF graphs from question 1. And we chose a log normal distribution, so we had to find the parameters lambda and zeta. And as you can see, after transforming the curves, it shows a much smoother trend. It goes from being a discrete function to a continuous one. And it closely follows the curve, so we believe it is a good representation of the data. And this graph just shows everything from steps 1 and 2 together. I mean questions 1 and 2. Addressing question 3 now. So for question 3, we had to look at the temperature and salinity data. And we use the same procedure as for question 1 and 2 in finding the the normal CDF and the transform CDF. And as you can see right here, that the normal CDF, which is in blue, and the red CDF, which is in the log transform CDF, is in red, and they closely follow each other. And the same for the salinity graph right here, along with our calculations. The reason we chose the log normal distribution once again was because we researched it, and this method of distribution is commonly used for represent the physical world. It's used for parameters or like things that are only for numbers that are positive. And in this case, salinity can only be positive, but temperature can vary from negative to positive. But our values for temperature in positive, so we found that proper to use the log normal distribution. And as you can see, the graphs closely follow, so we chose the right one. Now moving on to question 4. Question 4, we had to graph the extremities of the LNTC values and the temperature values and the salinity values. And how we went about this was we created a MATLAB code which had to compare the empirical and the exact PDFs and CDFs for our extreme values. And what we did was we took a sample size of 200 from our data and iterated that 1,000 times in order to find a maximum and a minimum value, not just for the actual graph itself, but for many different samples, so we could get a distribution of maximum and minimum values. We then plugged those in and created an artificial empirical CDF and PDF. And we then, after that, we used the exact extreme distribution function for the normal distribution, graph these exact PDFs and exact CDFs. And this is the one for the LNTC values for station 0 only. And these are extreme values for, this is the PDF and this is the CDF. And then we did that again with our temperature, this maximum minimum of the PDF and also the CDF. And then one more time for the salinity, PDF and the CDF. Now for question 5, was this video presentation and also to sum up our results and the external factors affecting the TC concentrations. And in essence, we found that the TC concentrations were smallest at the 0 station, and then bigger at the southern, and largest at the northern stations. And we account this for different populations of people on different sides of the beach, because human recreation and activities and like what they have and their pollution and their trash and everything, all that affects the water content and its quality. So the more human interaction with the water, the less the quality of water, which causes an increase or decrease in TC growth, which is why there, even though it's the same beach, there may be different concentrations of TC. And for the temperature, we saw that the trend is increasing TC concentrations with increasing temperature. Found this was because we did some research about the ideal growth rate of the coliform with temperature. And the ideal temperature is from 30 to 37 degrees Celsius. So within that range, the coliform really thrives. But our range of temperature values we checked only goes from 10 to 25 degrees Celsius, which is why going up to 30 to 37, increasing for our data sample causes an increase in TC. However, if let's say our data range was above this ideal growth rate and it was in the 40s or maybe even higher, this would cause the coliform to actually maybe hinder in growth or even to start dying from the temperature, which will cause a decrease with temperature with a decrease in TC, I'm sorry, with the increasing temperature. So the results would be flipped if it was above the ideal growth rate. And as for the salinity, increasing TC with decreasing salinity, that's the trend we saw. And the reason for this is we looked into it, and for organisms, they too also have an ideal growth rate within a certain range of salinity. But overall, most organisms, including coliform, the trend is that the more salt there is, the less they can survive, which is why if there's less salt or decreasing salinity, there's an increased growth of coliform. And one more factor that we looked into was the dying organisms, marine organisms. And what happens when a marine organism dies in the ocean is it releases a lot of compounds and it reduces the quality of the water, which could cause a sporadic concentration or deconcentration of TC. So the thing that we were looking at is maybe there's to explain the extremities in the data or like the randomness here and there that don't follow the trend is because of, let's say, a particular sample had more dead organisms, then the TC concentration would be higher because the water quality would be lower, versus maybe another sample for by chance has a lot of or less dead organisms, so the TC concentration there will be less, and that causes fluctuations in our trends, which causes the extremities in our data. And that concludes our presentation for group 13.